This conference will now be recorded.
Hello students, now I am going to give a demo on FIR filters, design of FIR filters using MATLAB. We are going to design the FIR filters using 5 types of windows, namely rectangular window or box bar window, Bartlett window or triangular window, Hamming window, Hanning window, and Blackman window. For each type of filter, we are going to generate 4 types of responses: low pass filter, high pass filter, band pass filter, and band stop filter. For each windowing technique, we are going to generate 4 types of responses, namely low pass filter response, the magnitude response of low pass filter, high pass filter, band pass filter, and band stop filter. So the main difference between FR filters and IR filters is FR filters are mainly non-recursive in nature, and FR filters have some advantages over IR filters also. Right. Now let us share your screen now and then explain about the design of these FIR filters. So this is a MATLAB program for the design of FIR filters using rectangular window. So as usual, you are using close all, clear all, and CLC commands. Then you are entering RP is equal to input of enter the passband ripple, RS is equal to input of enter the stop band ripple, FP is equal to input of enter the passband frequency, Fs is equal to input of enter the stop band frequencies, F is equal to input of enter the sampling frequency. 5 input frequencies you are going to enter. Then you are going to normalize them. Omega p is equal to 2 times Fp slash F, and omega s is equal to 2 times Fs slash F. Omega p is called as normalized passband frequency. Omega s is called as normalized stop band frequency. Then you are going to define two variables known as NUM and DEM, whereas where NUM is equal to minus 20 log 10 square root of RP minus RP into RS minus 30. So the formula for this order of the filter is minus 20 log 10 RP square root of RP into RS minus 13 divided by 14.6 into Fs minus Fe by F. This is the formula for the order. So you are going to separately design the variables NUM and DEM. NUM is equal to minus 20 into log 10 square root of RP into RS minus 13. DEM is equal to 14.6 into FF minus FP slash F. Now you are going to use seal of NUM slash DEM. You are going to use the seal command, which is going to round off to the order to the next higher integer. That is a seal command. So divide this particular NUM slash DEM and then use the seal command, which rounds off to the next higher integer value. Then you are going to use n1 is equal to n plus 1, increment n by 1. Then if remainder of n comma 2 is not equal to 0, n1 is equal to n is equal to n minus 1. So you are going to use a if loop here. You are going to use an if loop here. You are going to use an if loop here, which is going to round off to the which is going to make the filter only odd. Remainder of n comma 2 is not equal to 0, n1 is equal to n is assigned to n1, and n1 is n is equal to n1 and n is equal to n minus 1. So this if loop makes the filter odd, because why the order is odd means because there will be a center of symmetry in the odd coefficients. For example, if you take n is equal to 9 or n is equal to 11 order, capital N is equal to 9 and capital N is equal to 11, the impulse response coefficients will vary from, for example, n is equal to 9. If you are going to take, the impulse response will vary from h of minus 4 to h of plus 4, including the zeroth sample. Similarly, this impulse this one is also will vary from h of minus 5 to h of plus 5 for n is equal to 11. including the zero sample, like this. So there will be a center of symmetry there. So here you are going to use y is equal to Bhaskar of n1. Y is equal to Bhaskar, and Bhaskar is a command is used to calculate the Bhaskar window coefficient. Bhaskar is for rectangular window. Remember that. Bhaskar is for rectangular window. Y is equal to Bhaskar of n1. Then design this particular low pass filter. B is equal to FIR1 of n comma omega p comma y. FIR1 is an important command in MATLAB used to return the FIR filter coefficients. Takes into account order n, omega p the passband frequency, normalized passband frequency, and y window coefficients. Y is the window coefficients, and is going to return the FIR filter coefficients and store inside B value. Why are using here B only, not why not B comma A? This is very important because in IR filters, that is Butterworth or Chebyshev filters, you are using B comma A, but here you are using B only. Why? Because the FR filter doesn't have denominator; it has only numerator. Because they are recursive, they are non-recursive systems. Output depends upon only present and past inputs. There is a non-recursive system. Whereas in the recursive system, you have both numerator quotients as well as denominator quotients. In IR system, that is Butterworth or Chebyshev filters, is a recursive systems. So there you had both numerator quotients as well as denominator quotients. But here there are only numerator quotients, that is B is only there. That is FR1 of n comma omega p comma y. Then h comma o is equal to freq z of b comma 1 comma 256. So here this frequency response is Z domain is plotted. Why are once again here freq z of b comma 1 is there? 1 is there because the denominator is 1 there. Whereas in IR filters you had b comma a comma something. But here you have b comma 1 comma 2. There are some 256 questions that are there, and you are going to plot the frequency response for all the particular things. You are going to plot the frequency, use the frequency dictate command, and then plot the frequency response for all these questions. Then m is equal to 20 log 10 abs of h. Because you need to calculate the magnitude of all these things, you are using m is equal to 20 log 10 abs of h. Okay? Abs returns root of a square plus 2 square. 20 log 10 returns gain in dB. That is stored in. So if for each and every value of h, you are going to calculate the magnitude by using the function abs of h and then converting into dB representation. Afterwards, you are going to use subplot of 2 to 1. Plot of O by O slash pi comma m. You are going to divide the entire screen into two rows, two columns, first position, second position, third position, fourth position. If you divide the entire screen into two rows and two columns, there will be totally four positions. Okay, the first position, the second position, third position, and the fourth position. First position, what is there? Low pass filter response is plotted. Second position, 2 high pass filter is there. 2 band pass filter response is plotted. 2 band stop filter response is plotted. Like this. A plot of 2 to 1, plot of 4 slash pi comma m, x label, y label. Okay, x label of normalized frequency, y label of gain in dB, title of low pass response. Title of low pass response. So we are going to use this particular plot this low pass filter coefficients. Then you are going to once again use this. There is only one difference between low pass filter and high pass filter functions. B is equal to FIR1 of n comma omega p comma high comma y. So here previously you are using n comma omega p comma y. The only difference between the low pass filter and high pass filter commands is you are going to here use b is equal to FIR1 of n comma omega p comma high comma y. Then you are going to use as usual h comma o is equal to freq z of b comma 1 comma 256. Then m is equal to 20 log 10 abs of h. Subplot of 2 to 2. Plot of o slash pi. Okay, slash pi why you are using, because you are going to convert each into the integers which is lying between 0 and 1. You are going to use that particular command o slash pi comma m. X label, y label, title of this high pass response. Then for band pass filter, you are going to use define a band, that is omega n is equal to omega p space omega s. Then you are going to use b is equal to FIR1 of n comma omega n comma y. First define the band, then you are going to use this particular FIR1 of n comma omega p comma y. H comma o is equal to freq z of b comma 1 comma 256. M is equal to 20 log 10 abs of h. Okay. A plot of 2 to 3, plot of o slash pi comma m. So once again here then a third position, because you are using the third position, you are going to use plot this digit, and then you are going to use this particular command plot of o slash by comma m, then plot the band pass filter response. Finally, you are going to use b is equal to fr1 of n comma omega n comma stop comma y. Okay, previously you are used the n comma omega n comma y. For bandpass filter directly you are using n comma omega n comma y. Here directly you are using b is equal to fr1 of n comma omega n comma stop comma y, which is the returns the band stop fr band stop filter coefficient on source inside b. Then as usual h comma y is equal to fig z of b comma 1 comma 2 to 6, m is equal to 20 log 10 abs of h, subplot of 2 to 4, plot of o slash by comma m, all these things. Right. So this is about the logic of this particular FIR filter program using the rectangular window or Bhaskar window. Now let us run this program and then try to see the output. After running this program, we are going to enter the parameters here. We are going to enter the parameters in the command window. Now I will share the screen of the command window and try to let us let us enter this particular parameters. So we are going to give it as 0.05, 0.04, 1500, 2000, 9000. So this figure is generated. I'll share the figure screen to you. This is the figure window for this particular Bhaskara rectangular window. The first one is low pass response 2 to 1. First position, low pass response is plotted. Okay, low pass filter response. So it has so the x-axis has a normalized frequency varying from 0, 0.1 etc. up to 1, 0 is to 1. This one, y-axis we have gain in dB, so defined as 0, 20, minus 20, minus 40, minus 60, and minus 80. We have got a main lobes as well as the side lobes in this particular thing. You can see the side lobes also as a decreasing, okay, gradually, and then high pass filter response. It passes high frequency components, rejects low frequency components. The position is plotted in the position 222. Here also normalized frequency versus gain in dB. Y-axis is gain in dB. Third response is band pass response. So here you are going to use normalized frequency versus gain in dB once again. So you are going to pass the button band of frequencies that is there. Finally, you are going to use the band stop filter response. Okay, this is used to plot the band stop response. Here also you have the normalized frequency versus gain in dB. So this is the design of FIR filter using the rectangular window. In the study, in the fifth, in the completely fourth chapter will be dedicated. The fourth chapter in the DSP is generally dedicated to this particular FIR filters. There we will study about the different types of windowing techniques. What is the response in this case, and what about the mathematical representation in this case? All these things you will study there. Right. Now after this, let us proceed to the next type of window. Let us proceed to the next type of window, which is called as botlet window. That let us design the FIR filter using the bot. I'll show you share the screen and explain you the program for designing the FIR filter using the botlet window or triangular window. So this is the program for FIR filter design of FIR filters using the botlet or triangular window. Here the entire program is same. The entire program is same. Especially only difference is here. That is y is equal to Bartlett of n1. This is the only difference. Previously, I have used y is equal to Pascal of n1. Here, you are instead of that, you are going to use here y is equal to Bartlett of n1. All the remaining things is same. There is no change in the program. Entire program is same for all the types of windows. So only this command is change is there. Remaining things are same. Low pass filter, high pass filter, band pass filter, and band stop filter responses. They are ratio is same. All the same. Okay. Right. Now let us. Uh, so is this is this program is going to return the Bartlett window. Bartlett window is also called as triangular window. Triangular window coefficients. Now we are going to uh, run the program and then enter the parameters and then see the output for the Bartlett window case. Here also you enter the same thing. I'll share the screen now. Here also enter the uh, same parameters as you entered before. Now I will show you the figure window which is generated after entering these parameters. This is the figure window, Bartlett window response that is generated after entering the parameters. First one low pass filter, then the normalized frequency is from 0 to 1 and gain in dB, and high pass response going to pass only the high frequency component. So the normalized frequency is varying from 0 to 1 and gain in dB in the y axis. Band pass response is going to pass only certain band of frequencies. Okay. And finally the band stop filter. Band stop filter is going to reject the required band of frequency. So this is about the Bartlett window response. Now let us proceed to the next program. Design of FIR filters using Hamming window. So this is the program for the design of FIR filters using the Hamming window. So Hamming, Hanning, Bhaskar, they're all names of the scientists who have invented these types of windows. So here the entire program is same, especially that we have got here y is equal to Hamming of n1. This is the program. This is only the different here. So instead of there you have used Bhaskar in rectangular window and Bartlett in the case of triangular window. Now you are going to use for the Hamming window. You are going to command known as Hamming of n1. Remaining things are same: low pass filter response, high pass filter response, uh, band pass filter response, and band stop filter response. All these things are same. Right. Now let us run the program. Let us give the uh, let us run this give the inputs and run this program. So this is the figure window for the design of FR filters using the Hamming window. You are going to see that the low pass response, which is going to pass only low frequency components, having some main lobes and side lobes. X axis you have normalized frequency versus gain in dB, and second one is high pass response, which is going to pass only the high frequency components and reject the low frequency components. Once again, you have the normalized frequency versus gain in dB. Next, third one is band pass filter response, which is going to pass only the required band of frequencies to be passed. The x-axis is normalized frequency, y-axis is gain dB. Finally, the band stop filter, which is going to reject the required band of frequencies and pass the other components. So here also this is normalized frequency versus gain in dB. So all these things are there: low pass filter, high pass filter, band pass filter, and band stop filter response. Using the FR, this is the design. This is about the design of FR filters using the uh, Hamming window. So there are two other types of windows. Similarly, you can proceed for that. In the laboratory, you can proceed for the remaining two types of filters, namely Hanning 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 window and Blackman window BLACKMAN Blackman window. These are the other types of FIR filter windows. So you are going to observe that what is the observation that you can make from all these types of windows. The response is different in each case. The response is not identical. For example, if you compare Bhaskar window and Bartlett window, the response is different. So because the orientation of main lobes and the orientation of side lobes is different. Similarly, if you compare Bartlett window and Hamming window, the response is different. Low pass, high pass, and band stop response is different. The orientation of this particular response is different. Okay. So we can, so in the similar way you can proceed for the other types of two, which are the two types of windows, namely the Hanning window and the Blackman window. So you need to plot totally find the responses of low pass filter, high pass filter, band pass filter, and band stop filter for all these types of windows. Five windows: rectangular or Bhaskar window, Bartlett or triangular window. Third one is Hamming window, Hanning window, and the last one is Blackman window. So you can go into this. So for all these cases, you will be generating the magnitude response, right? So in the next experiment, we'll see about the demo of the sixth experiment. That is actually sixth experiment is consists of two parts. 6A is circular convolution using DFT IDFT method. 6B is post spectral density of a sequence. These are the two things, two programs that you are going to uh, see the demo. Okay, thank you.